Class J, microscopes, telescopes, and eclipses, or optical instruments. We're going to dedicate this class to inventors as we look at a variety of inventions that involve optics. I hope you enjoy this class as we look at a lot of different things, neat inventions. Okay, Chapter J, microscopes, telescopes, and eclipses, or optical instruments. And we're dedicating this chapter to inventors. Let's go over inventions and some that we've already covered. The pinhole camera here, a one-to-one correspondence between the object points and the image points, and a picture taken by my students of me way back a long time ago, around 1985, where I had a camera, ripped it off my sister-in-law Debbie, and took out the lens, smashed out the lens, replaced it with a pinhole. And for 20 years, I was able to then take a picture and use this Polaroid camera, so pull out the film and develop it right there on the spot and send it around to class. Although I had to maintain 60 seconds of being still, I think here students wanted to take me. I usually take a student's picture every year, but I think they said, no, you get up there. We're going to do one with you. And so this is the curtain that we have in the back. And there, the quad is right out there through there. Then I showed the infinite depth of field by taking a picture from my old office, which is now a machine shop down at the bottom the engineers use, and Rhodes Hall down at the bottom, ground floor. And I took a picture looking out at the parking lot here. And this is where now Robinson Hall is built in here. And you're looking at the cars are in focus and also the screen. Amazing, like infinite depth of field. And then section 2, the camera, we did as an optical instrument, an invention. And we have here lots of angles of view. This is your Biltmore house. And it looks very, very nice pictures here that show different focal lengths and angle of view. And then 3, we did the eye. And here, with the eye, I just want to comment as I'm reviewing the things that we've covered. Red eye is when the light penetrates into the eye from the flash and it hits the back of the retina and then comes back and it looks red. Notice here there's a surface reflection. This reflection in the eye, this is the cornea, where you have the light bulb reflecting from the convex surface of the cornea. So you have here the little white spot, which is the corneal reflection, and then the red eye is from the retinal reflection in the back. And photographers don't usually want to avoid this, so cell phones engineers design them so that when they do it, and expose film a split second later or something, that you might want to minimize the red eye. But photographers in the past have simply detached the flash from the camera and hold it to the side so the light doesn't come straight back. Although in my case, I like to get this. See, I go for red eye. So here are my 3 kids, and all 3 got red eye. So Chris has got red eye, Evan's got red eye, and here we got Francis with red eye. All red eyes. And next one's the magnifying glass. And for the magnifying glass J4, we're going to head over to the drawing board. But before we do that, this is coming from a little application I wrote in 1990 using a tool. It was called Toolbook, one of the first multimedia authoring systems back in 1990. So I think that was Paul Allen, Bill Gates' close friend. Bill Gates, of course, founded Microsoft, and then Paul Allen did this toolbook thing right when Windows 3 came out. J4 is a magnifying glass. Now, the magnifying glass, let's look at first how close something can get to the human eye. So I'm going to put here a line which represents where we could also say here's where we're going to put an eye, and the closest that you can get is, well, the standard is 25 centimeters. That's reading a book at 10 inches. So this would be what's considered the normal. I'll draw a ray through the center of the lens system here. And you can look at this angle here as alpha. So when you look at something close up, the angle, and this I'm going to call this D, because some kids kids can go long, shorter, 15, 10 centimeters. But the tangent of alpha would be, here is the object height over, let's say D, where D can be anything, so that we can consider people eyes that are above average. Now, what the magnifying glass does, it lets you get closer, bring closer to the eye. So we can bring something closer to the eye, and what's going to happen here, it's going to move the image farther back so you can see it. Now, if the light comes out parallel, that's fine, because the eye can then do the rest of the job. But notice that this angle here is a steeper angle because you're closer. So the tangent of beta, this is the same object height, HO, but now the HO is over, this would be at the focal point, is over F. So if you look at these and use the Paraxial Approximation, where this is your alpha, tangent of alpha is alpha, and tangent of beta is beta, then to compare beta to alpha, see what the magnification is, you would have H object over F, and then for the alpha, H object over D, the D flips over. So this magnification would be D over F. And you can consider this to be an angular magnification, that the angle, since here, if you have an image that's infinitely far away but infinitely tall, so the angle is the key thing you want to be looking at here. So this is the beta angle in there. That's a steeper angle than that alpha one. So D over F, it's a magnification. But it's possible to actually bring the object closer, and if you're closer, the idea here is what we're going to do is bring the object in closer, so that when you look at, say, your rays, you're putting this back here, where's the closest that you could focus on. So in this case, the eye has to work a little bit harder, because remember, when you focus at infinity, the eye is relaxed. Here the ciliary muscles are pushing in a little bit to get you more curvature of the eye lens to see closer, but that's going to get you a little bit better magnification. So in this case, this here is your image distance, and your focal length is going to be to this point here. So let's say, yeah, the main thing here is that you are between the focal point and the lens. if you're at the focal point, then this goes off to infinity. The light rates are parallel, like in the above case. And as you slide toward the lens, this becomes less magnified, so that when you hit the lens, it touches it, the virtual image is right behind you, the same size. So let's look at this for a second. This case here, this SI, if I make that the D, the closest I can approach, and since it's a negative space, the SI will be a negative D. All right, I'm setting this problem up like this. So therefore, 1 over F, which is 1 over S object plus 1 over SI, what happens here is we replace the 1 over SO here. We can, well, I think in my notes, I called this SO, I called it U. So I call the distance from the lens center to the object I call it U in the notes. So let's just keep with the notes. So this is 1 over U plus 1 over, and that's the minus D. We want to find the magnification, and the magnification in this case is going to be given by, this is your magnification. You want to be careful here. We're doing angular magnification. So if we do angular magnification, or we're doing with the angles, then if we look at this situation here where this is the object, and I blow up the triangle, so this is the angle beta, then this distance here I'm going to call U. This is the height of the object. But if you remember correctly from before, that the tangent of beta is H O over U in this case. So when you do that, replace the F, where here we were the distance F away, here we're U away. The more general magnification formula is going to be D over U. But I want to get rid of U, so I have everything in terms of F and D. So here, I really want this. I want 1 over U, which is 1 over F plus 1 over D. So that's what I want to go in. This is 1 over U. I want that in here. So when I multiply by the D, I then get D over F plus D over D. And this is the famous equation for the magnification, which is like your optimum magnification. It's what we had before, D over F plus 1. And like that's considered the best, because by bringing that image as close to the possible as possible that you can see, that's like the best deal. Your eyes work a little bit more. So that's nice. And here from the 1970s, Jim Hutton, Detective Ellery Queen, and his son, Hutton, is an actor. Also, you probably have seen the son in movies. You can Google Hutton. J5, the ophthalmoscope. This is very close to our discovery with this homework problem with looking at the bug in the tube. The answer was a half-silvered mirror where the light came in, reflected off the mirror, and half went through the mirror, which I'm not showing here, hit the bug, came back, and then half went up to the bulb, which I'm not showing here, and the other half went to the eye. So this is how we can look at this invention, the ophthalmoscope, where the bug is replace the bug with the patient, and the patient's eye here, the retina's back there, and then here the light is placed at the focal point of this lens so that the rays go out parallel. Some go up straight up, but then half go this way, go into the eye, reflect back, and then come this way through the half-silvered mirror. Some will reflect back down. And then here there's some lens to help focus on what you're looking at, and the doctor. So very, very similar to the bug problem. J6, the slide projector. Here's a slide projector, and we're going to go to the drawing board and do this on paper calculation. But I just wanted to show you that here, these slides are 2 inches by 2 inches. All right, it's like about like 2.5 centimeters per inch, about like 5 centimeters by 5 centimeters. And the slide's going to be in here, and then there's a light source back there that's going to shine the light through, and here's the bulb. And I'm going to estimate, from there to there is about, say, 7, 8 inches, 8 inches or so. Make some approximation just to get an idea of some distances, and that would be the SO, the object distance, and then this focal length. And then for the image distance, I'm going to use the auditorium. So this is the auditorium, the 125 in Rose Robinson Hall, and the projector's way back here, and this is about 40 feet. All right, so it's got to go from there, to hit this panel, and there's the slide. John Warner, photographer, did a wonderful job here to get the slide in the picture, me in the picture, some demonstrations in there. And Marion Epstein, the one back here, she hired John Warner. She worked with the PR folks at UNCA to get some nice pictures taken. And so we're looking at 40 feet. So we'll be using this distance, 40 feet, and we're going to figure out what the focal length is, like as an engineer, if we had to design what focal length are we going to use. And here I had to get a special lens because this is not your traditional throw distance for a slide projector. It's more like 20 feet or so. And this 40 feet, we had to get a projector with a bigger lens is capable of making this bright enough on the screen. The bigger lens gather more light from the light bulb. Okay, now we're looking at a problem here with the slide projector. So we're dealing with the slide projector here, and for the slide projector, what you want to do is you want to project something that's far away. So the secret is to get close to the focal point. When you're close to the focal point and you do your rays, then you're way out here, and that's what you want. Now the slide here, if you go in like that, it'll come out like this. You basically have to turn the slide around the other way. If you flip the slide the other way, then this will go flip, and the other one will flip, and you'll have the right orientation. I remember when I had my first job as a teaching assistant, the professor, Dave Falk, saying, be careful how you put the slides in, because if you put the slides in wrong, it'll be upside down. You got to put them in, you got to turn the slides upside down. So when you do this, you got here your F, your focal length. You got here SO, your object distance, your object height. This is capital F, the focal point. And this would be your image distance to go out there like that. And this is your image height. Now, a realistic problem here, if we were to look at the slide projector. So if you look at the slide projector, like the picture of the slide projector, and you have something like here that it has a lens out in there, and you could see the slides, you can estimate, you can make an estimate that we're talking here about 8 inches. And we're doing an estimate here. We're going to estimate things. You can actually get the slide projector out and measure it yourself, but I'm saying going by the picture, this is about 8 inches or so. So that means SO is 8 inches, 20 centimeters. All right. And the distance to get to the room, I'll use the auditorium in Robinson Hall, that's 40 feet. And when you do that 40 feet, I mean, we're talking like 12 meters, 40 feet. If you divide by 3, you get 13, like 13 yards. And so it's about 12 meters. And that would be 1,200 centimeters. It was so far back, the 400 feet, that I had to buy a better lens that had bigger area so it could project, because usually a slide projector's not that far back. So here, we'll go ahead and do some math here. 20 times 1,200. So this would be taking your 1,200, adding 20, 1,220 over 24,000. And if you look at this, this here is 6,1. Well, could have left the 1,200. And if you flip that, you get here 19.67. Remember, everything's in centimeters. So that would be a 200 millimeter lens. Nice. Little calculation there. J7, the Fresnel lens. I love this story because here's where the necessity is the mother of invention. They're trying to make lighthouses and mirrors or ways they want to get the light. They want to get the light out to the ocean or to the sea or whatever, so the ships can see where to come in. So concave reflectors, these things can get big, popular design. And then if you have a lens that's bulky, and he figured out a way to make the lens work where the lens was not bulky. That is just amazing. Fresnel, and also Fresnel is known for Fresnel diffraction, also a theoretical physicist. So here we have an inventor and a theoretical physicist, and today we're going to see this is a common theme, that you have some physicists and astronomers that invented like telescopes and like they're inventors and also astrophysicists. So here you have a theoretical physicist, marvelous with calculations, Fresnel diffraction, which we'll study later in our course. And here, the idea that when you have glass, the refraction takes place at the interface. So all this glass is not needed. It's like a waste. The magic takes place when you go from air to glass and glass to air. So suppose we had cut this in half. So we just have a planar and then a curved part. This is still converging lens. All right, not as strong because this is the neutral surface, but still converging. Now suppose I take out all this glass out and save all this glass. This will still work. This thin thing will work. But that's a little bit hard to construct. But suppose we broke these and flattened them out like this. Well, that's not quite what you should do, but it turns out that it's still good quality. It still kind of works. So now you can make a lens with little parts like this, and that's what is the Fresnel lens. Like, amazing. See, like you build up this, see these like circular parts here that you can consider here is like circular ridges, and those ridges, and this is then a very powerful lighthouse lens system. And you put like a candle in the old days, you put a candle in the middle there or something, or some kind of flame or light bulb now when you have electricity, and then put that the focal length, and the light will come out parallel here and go out far out into the sea, so that ships coming in can identify where to come in to port and to land. Amazing. Here is a lighthouse in North Carolina. This is a trip I made to Beaufort, North Carolina, and not far from Beaufort, North Carolina is a 163-foot lighthouse, and that is at Cape Lookout at Harker's Island in North Carolina. Nice. See? Very good. Here's Fresnel lens in the theater. And see, there's those concentric circles. See, there's ridges, and that's a thin lens compared to the bulkiness that would be if you had the original, glass before you basically got this thing compressed. And then you can press these out on plastic. So here's plastic. Here's like 25 Fresnel diverging lenses, and you get 25 images of me standing there. A little bit hard to see, taken by Wendy Newman, a Nashville professional photographer. And here, she zoomed in with my daughter, there's 9 Fresnel lenses here, these little ridges. If you put your thumb on here, you can like feel the ridges, concentric circles. And diverging lens means that you're going to see something smaller. And because of that, you can see 9 of them. There's actually 9 lenses here, 9 Fresnel diverging lenses. And on the sheet, it's like 5 by 5. There's 25, but here we're looking at a subsection, and my daughter standing behind. You can see the 9 virtual images of my daughter. That's Krista. The overhead projector, J8, and here this is like a museum piece now. Not really used that much, but this is actually a Fresnel lens. This lens here is flat, and you want it to be flat. See, nice flat lens there. You can put your transparency on. Down in here, they have a light source, and they have that at the focal length for this lens, so that when it hits this lens, it goes up parallel through that overhead sheet. And it might probably have a mirror back here that would direct light back up to the Fresnel lens. They're not waste light. And then when you look at this as your object, then there's another lens up here that you're going to be making an image on the ceiling, a real image on the ceiling, but there's a mirror here to flip it over to the front of the room. And that's a very nice invention. So here's a couple of challenging things for you. If you back up away, the teacher backs up away from the screen, this will get larger according to the physics. And how does this have to go? Turn this to go up or go down? Most people don't remember, they just guess. But if you were to move this away, you see, here's how you can figure this out. This is the object, but this object here has to be, if you look at this focal length up here, if you want to shoot something far away, the focal length of this thing has to be just not too far away from here. You want to be to the left of the focal length, the usual setup, or you want to be here, say, close to the focal length, because when you're close to the focal length, that's when you get a real image. As long as you're greater than the focal length, you get that real image that's going to be projected far away, and then that mirror flip it so it goes far away in the class. So your focal length, it's going to be like about there. But if you were to back away, then if you were to back away, you need to make that focal length, you need to go far, focal length needs to be lowered, so you need to actually lower this. I want you to think about this rather than me tell you what the answer is. I'd rather you think about, if you move this back or move this forward, what has to happen to this distance here, increase or decrease? And that takes some time to think about. And when you think about that, just remember, you do want to be looking at this situation. See, when you shoot something far away to be looked at, say, in the room, you need to have your transparency close to the focal length of that secondary lens, which is the one that's above the overhead, and that will get you something far away. So when you get farther away from the screen, when you move the whole projector back, and then this distance is bigger, then you need to nudge yourself a little closer to F so that this will be farther to the right. Remember that the closer you get to F, this thing goes more to the right. So I want you to think about that. Some challenging questions about the overhead, very, very subtle. Think about that. All right, they make for good GRE questions. J9, the microscope, and here we're going to go to the drawing board and do this, work this out for you. And now for the microscope, J8. The idea is to have a converging lens and another converging lens. And it's basically a similar property as the projector, you want to get your specimen close to the focal point so that we can have a magnification here. And then what you do is you have a magnifying glass where you're going to look at this as a magnifying glass. So if this, say, go like through there, and here, let's say we have focal length that's a little longer like that, then these, you know, make somewhere down here, say some enlarged. This is be your image. That's final image. Say here is what you're looking at, the magnification. So your eyes, you know, over here, looking down. So you get the magnification at two stages. You get one magnification due to what's called the objective lens, and then the magnifying glass is kicking in, which here we can call that the eyepiece or the ocular. You see, your magnifying glass is your simple microscope, and this is called the compound microscope, and usually what we mean by a microscope, we mean one of these things. So you can label, you know, things here. This is, you know, F. This is the object, you know, distance 1, because you have two lenses. This is going to get you your image distance 1. Then you have the old trick where you have your D, your distance. This is going to be, you know, D minus SI1. That becomes the object distance for the second optical element. And then this here is going to be your image distance for the second, and that's going to be a negative, since that's a negative space. You might label this image 2, and then this is the image 1, and this is the object here 1. And this image 1 height becomes the object height, you know, for the second analysis. So this would be like F2 is out here. Here is F1, the F1s. And, you know, if you want, you can put another F, you know, somewhere here for 2, if you want. So everything is labeled. Now I have a nice picture like this in your book, but I like to try to draw everything if possible, because that's how you learn things. You learn better. But, you know, this is all neatly drawn for you in the book. So what we're going to do is, we know that the distance SO1, you want the SO1 to be greater than F1, but you want it close. So I'm going to say yes, but we want it to be close to F. It's as if this SO1 is equal to the F plus an epsilon. In other words, if you have this distance F and plus a little epsilon there, that's going to get you like the slide projector, you know, this is going to be larger and projected, you know, farther away, but not too far. And that's some of the design characteristics we're going to have to worry about. What I'm going to do here is pick SO1 to be 1.04 F1. So that would be a little epsilon is in there. This is SO1 is a little bit more than F1. Like the epsilon's like your 0.04, you know, F1. So this can be written as 104 over 100 times F1. It's very close to F1. So the epsilon there, if you want to think of this as epsilon, you know, 4 hundredths F1 is the extra, the little extra piece we're putting in there. So if we do that, then 1 over F is 1 over S object 1 plus 1 over image 1. And that's going to get me 1 over F1. Now the SO1 is 104 over 100, so this will flip to have 100 over 104. When I put in here, I'm flipping this, 104 F1 over 100, so it flips. All right, so because I want 1 over this, and that's going to be 100 over 104, F1, so there it is. And then I have plus SI1. So this is going to be 1 over F1, 1 minus 100 over 104 is 1 over SI1. And here, if we do this, this is going to be 104 minus 100. So that's going to get us 1 over F1 times 4 over 104 is 1 over SI1. And that means the image distance here is going to be 104 over 4 F1, because we're flipping everything. And here, this is 100 and, no, this would be, let's see, 52 divided by 2. And this would be 26 F1. So that's, it's pretty far away, compared to the focal length is like 26 of them away. So the next step is, in my design, I know now where this is. I want to know what my constraint is on D, so I look at this. If I turn it sideways, here's the eyepiece here, and the other lenses like Dan and here usually can change them. They have some choices. So around here someplace. So this is the D, and this has to sit on top of a desk. All right, so we're looking at, say, here to here is D. So I'm thinking here, 150 millimeters. I'm just going to pick one that would seem to be fine within the ballpark. 150 millimeters. The D to be 150 millimeters, 15 centimeters. Now you got to be careful that this focal length here has to be to the left of this intermediate image. So we do have some numbers though. We do know where this is. This is 26 F1 to the right. So I need to have the 26 F1 to be less than 150 millimeters. So here, if I pick, say, F1 to be 5, all right? Then this 130. So in other words, if F1 is 5 millimeters, it's a small focal length, then 26 of them will be 130, and it fits the engineering spec. So this is kind of neat how we're doing this. We're doing a lot of engineering here. We're basically engineering a design. This is a design problem. We're trying to design a microscope that's reasonable, sits on the table, and biologists can use. So now we're starting to put pieces of the puzzle together, all right? So at this point, I think we want to summarize what we have. We have the first focal length to be 5 millimeters. We have the object distance is 1.04 f1, which now when we plug in, we'll get 5.2 millimeters. So here, if this is your 5 millimeters, this is like 5.2, real close by. And then the S image 1, which was the 26 f1, is going to be your 130 millimeters. What's the magnification so far? And here we have the linear magnification, the regular formula, SI1 over SO1. So this is minus 130 over 5.2. And that's minus 25. That's pretty good. It's like pretty good magnification. Now we're ready to set up the next problem, where we're going to figure out what happens with the ocular when the ocular kicks in. So that's going to be this formula. 1 over f2 is 1 over s object 2 plus 1 over image 2. Well, here I need to have this focal length to be bigger than this d minus SI1. All right, well, let's put some numbers in. We now know that this is your 150, and we now know that this is 130, so that means this little piece is 20. So 20, in other words, this is going to be 1 over 20. All right. And I don't know what the image distance is going to be, but here I have to pick the f2. Remember, the f2 has to be chosen to be larger. F2 has to be larger than the SO2 so that I can have the magnifying glass situation where the object is, between the lens and the focal point. So here's where engineering design comes in. I'm going to pick something close. I'm going to, if I pick 22, I'm going to pick f2 to be 22 millimeters. So then this is 1 over 22. All right. So that means 1 over SI2 is 1 over 22 minus 1 over 20. So this is 20 minus 22. 20 cancels there. I got 1 over 22, and then the minus sign, 22's cancel over 20. And I'm glad I'm getting a minus sign because I know that this is a virtual image back here, and it's going to come out negative, which is good. So this is minus 2. That's minus 2, and that's going to be divided by here. Well, let's see, let's keep the 22 and keep the 20, because if I cancel here, I get minus 1, and this will be 2, 2. In other words, cancel this will be 1 over 10. So 10 times 22, that's nice. And then if I just flip that, SI2, I get minus 220 millimeters, and that's in negative space, so that's over to the left somewhere. And then the magnification for the second lens is the SI2 over the SO2. Now this is minus 220. Notice the two negative signs will cancel because magnifying glass does not invert. And what is SO2? Well, SO2, if you remember, is the 20. The 20, SO2. So this is going to be 220 over 20, and that's going to be 11. Nice. So the total magnification, which is magnification 1 times magnification 2, the first magnification that we got, minus 25. The second magnification we got here, 11. And 5, 2, that's it, man, look at that. Minus 270, wow. Wow, that's a cool magnification. That's some serious overall magnification for our microscope. And here, I wanted to point out the choices. Like you can like turn this and like change your objective, like your eyepiece on the other end. So you can then change these to see like which one you want to do. So see the dimensions here. It's about like kind of dimensions that we worked out. So we have a design, nice engineering design problem here for the microscope. Very nice. J10, telescopes. A, refractor. So the refractor telescope has a lens on each end, and often these powerful telescopes will have some kind of sighting next to it. But the idea here, if you look at the telescope, this is objects can be far away, like the moon or stars, so you have no control over that. But the principle is going to be the same. We're going to look at a magnification, based on using a magnifying glass. And let me show you how this idea works. This is also called the Keplerian Telescope, after Kepler. And if we look at the situation where we have the two objective and eyepiece, here, the secret is to put the focal points to coincide, and I'm going to show you why. Here's F1, and here is F2. And let's say we're looking at like something coming in from the top of the moon or something, it's coming in like this. This is going to focus in the focal plane. That's where things are going to focus. When you're at infinity, you're talking about the focal plane. Now, since this is at the focal plane, this is where that ray is going to be. This can become the intermediate source for the second lens, and I'm going to go draw straight through ray 2. And now you can see the magnification. So if this is alpha coming in here, this is your alpha, then this is beta. And if you're looking, see here, the top of the moon, so if that's like the moon, then here, we're talking like there's the moon, like it's upside down and bigger. So you can see very easily how this invention works. And for the magnification, well, if you looked at this alpha and say this call this common here, just call that y for a second, then the tangent of alpha is y over F1, and the tangent of beta is y over F2. So if we play the same game as we did with the magnifying glass, this is your alpha by the approximation, this is your beta. So if you take, say, the beta, the bigger one, and divide by the alpha, you're going to get here the beta is y over F2, and the alpha is y over F1. The F1 comes upstairs, and we're going to put a minus sign in front since it's upside down. And you can also, for the 1, you could make that here objective and make this eyepiece. So you can have this. So now you see that it's important to have the objective. This is the objective, and this is the eyepiece. It's important to have the objective focal length bigger than the eyepiece focal length because the ratio is the magnification. It's very, very, very nice. Now, let's look at Galileo. So this is B, Galilean Telescope. Now the telescope was discovered in the Netherlands. The story goes that Galileo was told they invented it and he promptly made his own. And the one that he made was very interesting. He had a converging and a diverging lens. We'll look at that in a second. And I always wondered if you had a great inventor today and you just told them something that was not true. Say someone invented in another country how to walk through a wall, and then they would say, oh, if they did that, they must have done it this way, and then go ahead and proceed to make the invention. So let's look at this here. The alpha is the same alpha as before, and if you go ahead and have a y, like we'll put the y here, then here's your focal length. This focal length is negative, so what we're doing is we're have the focal lengths coincide again, but because it's negative, we move it to the left, so that the D here is going to be the long focal length, and when you then add it, you can use the same formula. You know, D is F1 plus F2, but since F2 is going to be negative, then it's going to be less than F1. Now, notice that the ray 1, this ray here, actually is we called it ray 2, the one that goes through the center. It would go here. And I have another ray here. Any ray here is going to go there. So any ray, if you forget this, any ray here coming in here is going to go there. But I picked one that goes through the center so that this one wouldn't be deflected. So this would be actually the ray that actually does go through both. And then here, since this is diverging the rays, I can then use this as a guide to make this one parallel to this. And that's my outgoing rays. And that's going to, this by the way, also defines beta, because this one goes through the center, it doesn't bend. But once when I have that beta, I know tangent of beta is going to be the y over the F2. It's in the book there. And if I look at the alpha, that's y over the F1. So tangent of alpha is y over the big, because this is a big triangle here, over F1. And if I do the same approximation, this is alpha, this is beta, then when you take beta over alpha, you're going to have your beta is y over F2, same thing, and this is y over F1, the alpha. Y's cancel and you get the flip at the F1 over the F2, and that's what we did. That's what we had before. This is the ocular over the eyepiece. That's what we had before. But we put a minus sign in for the magnification, and let's go ahead and do that again. And the reason why we should be consistent here is that for this case, there's no flip. See this alpha coming in from the north, and see this beta coming from the north. You see, that's going to go into the eye. See, in other words, if the eye is looking back, it's coming from the north. It's coming from the north. That's not the case here. When I look from the eye, I'm looking down. And here, it came from the top of the moon. So the top of the moon is down here. So the Keplerian Telescope is going to flip things, and the Galilean Telescope will not. So this nice definition applies both telescopes. Very, very nice. Are you amazed how these scientists, who we normally think of as physicists or astronomers or astrophysicists, they're inventors? You know, Kepler worked at making telescopes here, Galileo, and Sir Isaac Newton. So we have the Newtonian Telescope. Sir Isaac Newton. There he is. So let's look at this. But before, let's talk about these scientists and what is science. So here you have astronomers or astrophysicists. I mean, Kepler starts out as a mathematician, like a mathematical genius, but applies it to astronomy, all right, and discovers the law of ellipses, three Kepler's laws, empirical laws, laws of ellipses, the law of equal areas and equal times, and the law of periods. That the period of a planet, if you square that, it is proportional to the distance cubed from the sun. Galileo, the Galilean Telescope. So these folks invented telescopes. They would work the telescopes. Newton. And here, I like to just, pause and talk about these scientists who were astrophysicists, which we call today, and also inventors and architects of the scientific revolution that happened in Europe in the 1500s and 1600s. This spanned almost 2 centuries there, or a good century and a half, say. And here they help us understand what science is. They help me understand because, see, in grade school you learn about science being control variables and hypothesis, and yeah, that's true. That is science, but it's not the only thing that science is. And just to show you the problem here is Kathy Wantley, Professor Kathy Wantley, I brought on at UNCA, closest thing we had to a rocket scientist, nuclear physicist from Duke. And Professor Wantley had a kid that needed to help in her school project, and like, what is the scientific method? And Mama said, I could help you with that. And Mama's a nuclear physicist, right? And when she helped out Katie came back home and said, look, Mom, I got a D or something. And see, this is the problem. The teacher wanted the control variables and hypothesis, and here's a nuclear physicist, a rocket scientist, right? And she knows what science is, all right, better than that teacher. And her answer wasn't accepted because of the rigidity of the educational system. What is science? Well, here is the scientific revolution, and here are the big five: Copernicus, Brahe, Kepler, Galileo, and Newton. And here Copernicus taught us that models, simplicity of models, is important science. When you put the sun at the center of the system, all the motions are understand much easier. And that's going to be the case, see, because at the time they thought the Earth was the center. So by the model, Copernican model, you put the sun at the center and everything simplifies. So models are very important in science. Tycho Brahe, the guy that spent 30 years without a telescope, because it was before telescope time, where he's mapping all the like stars, where they are in the sky and where the planets are. Interested in casting horoscopes, by the way, and seeing with Kepler on the side. So science is kind of mixed with horoscope and astrology back in those days. And the idea of data, good quality data, very, very important. Taking data, important part of science, experimental measurement. And then Kepler, the mathematician, Tycho Brahe basically brought him on as a mathematician to help him understand the data. And this mathematics. Kepler uses mathematics to get the equation of the ellipse to fit the data. So he fits the data for the Mars, planet around the sun, going in an elliptical orbit, and very close to a circle, but a little bit elliptical, and can match that data, good mathematics. Now, Galileo is known for a lot of things, but one of the things is the invention of the telescope. Of course, these others three of these others worked with telescopes: Kepler, Galileo, Newton. But the idea here is the instrumentation, that with the telescope you can actually see moons of 4 moons of Jupiter, which we now call the Galilean moons, and rings of Saturn. An instrumentation, very, very important in science. And then Newton, who did so many things. I want to stress, though, here the unification, that the apple falls to the ground and the moon goes around the earth because of the same force, the gravity. So they thought in the old days there was 2 kind of forces, one for the heavens and one for the earth, terrestrial versus celestial, where Galileo did work with terrestrial, rolling balls down inclines and stuff, gravity near the earth, and then Kepler did the celestial. But Newton's saying no, it's the same force. It's the law universal, called the universal law of gravitation. And Einstein was fascinated by this idea, and going for unified field theory today and string theory is trying to do this unification idea, take it to the final, hopefully, version where all the forces in nature are united in some elegant way. So that's what science is. See, and to just let these five, help us understand with science, you can't go wrong with science. And here I like to pause for a second and talk about physics genealogy. I love genealogy. I was fascinated by the family tree when I was a kid. And I was amazed that on the internet, we have some folks that are doing physics genealogy. And go ahead and click on that and pull that up. And physics genealogy, they go and track down like who taught who over the years. This is amazing. So this is already done for me. Galileo here had these students, and then look at this. You get down to Isaac Newton here, and then Isaac Newton, you're now in England, and you keep rolling down here. Look at that. That's amazing. And then here, look at this. John William Strutt, known as Lord Rayleigh, famous physicist. And then if you leave England and come over to, folks come over to the United States, folks students teaching at Princeton, teaching at Caltech, or here at Princeton or MIT. And here, Carl Taylor Compton, brother of the famous Arthur Compton, who discovered the Compton effect, and his brother got the Nobel Prize. This is the older brother. And if you go through here, you find Sam Treman, elementary particle physicist at Princeton. And then my advisor, young Kim, Dr. Kim, Professor Kim at Princeton. And then after that, comes me, and then you're down there. So like, this is amazing. You can trace yourself back to Galileo here and teaching. Okay, so let's find where we are. Not there. Okay, there we go. So for the Newtonian telescope, what Newton did is he replaced the objective with a concave mirror, and then had this little image here. But then to use a magnifying glass to get close to that, you're going to block the light. So he put a cute little mirror, little mirror in here that would make this go to the side, and then you could look to the side. So here's the concave mirror down there. So the light comes in, but there's a cute little mirror slanted there, a small one, but it comes in here, hits that, and goes back to that little mirror that then it kicks it up through the eyepiece, and there's the eyepiece there. And that mirror is real tiny, a small, cute little mirror. A little square mirror in there in this telescope. $10 telescope I bought when I was a kid, and it's fascinated. I loved astronomy. 1964, a best friend's brother had shown me with his Refractor Telescope Venus, Saturn, Jupiter, and craters on the moon. So with this telescope, I was very proud that I found Mars on my own as in like 8th grade, and saw the little disc, the little red disc. This is a 40 power telescope, about 40 times magnification, and it's about like a 2.5-inch mirror down there. Very nice. And then it took me a long time to find Mercury. I was at UNCA teaching astronomy. I was driving to school one day, and I couldn't believe it. I saw it in the sky, Mercury, and then Uranus, either way you say that, the seventh planet. The seventh planet I eventually found. So it's like I was excited about finding 3 of the planets on my own. My friends showed me 3. I've never seen Neptune. I guess that'd be the last planet since Pluto was kicked out. All right. And Earth, you just look down on the ground, you can see Earth. The Cassegrain reflector, and Cassegrain, was a Catholic priest, Lauren Cassegrain, that had this idea, and we're going to look at this. Now, the expensive one has hyperbolic and parabolic mirror. Of course, the cheaper ones will have the spherical, but then there'll be a trick that you can make the spherical one work pretty effectively by doing a little correction for aberrations with the Schmidt Cassegrain model, where you put a little deal here in the front. That's this thing here that helps distort the light in a way that cancels the distortion that you get with the concave mirror and these other mirrors, and you get good optics. And we could afford that. See, that's a UNCA telescope. In fact, we had more than one. And that's the physics graduate, Patrick Ragsdale there. posed for me many years ago. Beautiful telescope. So you have a little refractor there to help you get lined up. And then you have the big, this is the 8-inch, this has an 8-inch reflector in, and also compresses the telescope. The telescope is compressed with this kind of idea, see, where you, it doesn't have to be as large because you're folding it back. And we're going to go to the drawing board and work with this. So the Schmidt Cassegrain telescope, we got the light coming in, and we're going to hit here a curved mirror that's going to reflect things to acute convex. So this is a concave with the hole in the middle. And here we have parallel light going to this, you might think of as a nice little convex mirror, and then this is going to go out here like this and like be like focused out here. That is cool. So that compresses the telescope, and there is a corrector plate here because if you want to insist on using spherical cuts, then you get some aberrations, and the correcting plate fixes that. So here, these would have met, say back here somewhere, and this would be, where these would meet. There's a little better diagram in your book here. So here, where these would meet, this is your F objective. So that's parallel light would reflect to meet there, but gets intercepted by the cute little convex surface, and then comes out over here. So you have your parameters here. You have, somewhere like doing this is your objective, right? And then you have the distance between this mirror and that one, that's your D. And you might consider this as some U to get to this point. And then you put an eyepiece here. So this focal length of the eyepiece. You have the focal length here of the objective that collects the light. And there's a focal length here of the cute little convex mirror. So you have like three things going on here. And the Schmidt idea, Schmidt Cassegrain. So here you have 1 over F for the objective. And this is look at this as the first, we're calling this the first one. This will be the second optical element, and we won't deal with the eyepiece. That's going to be the magnifying glass effect, at the end. And then we'll look at here, I1. And then we have another set of equations for the cute little convex. This is object 2 and image 2. And then the magic formula here, how's the D work? Well, what you're going to do, you always use the same kind of idea that, what do you deal with the D? Let's just do this. SI image for, the object for the 2 is to take D minus SI1. Now, SI1 here may be, I don't care where it is. In other words, I set these things up in general. When I have two optical elements like this, and they're separated by D, I assume that this is going to be SI1. Then I take D minus that to get the SO2. And if the SI1 is somewhere crazy, I'll get negative signs, I don't care. I just set it up so everything's positive to get my equation set up right. This is correct. And then I don't worry. Now here, this SI1 is going to be it's going to be way out here someplace. So, all right. So this is D minus FO, and that's going to be negative, and it should be negative because the reason why that should be negative is because if it's out here, but here's your mirror, and it's facing the other way, you're in negative space. You're behind the mirror. See, so there's your convex, and this is behind the mirror. So that comes out right. But if you set things up this way with all positive, sines will automatically take care of it. So here's 1 over f for the convex. So in other words, we skipped a step here that since the object distance for the first one is going to be infinity, that this is going to be taken to be 0. So that SI1 is going to be f of the objective. So then I have 1 over FC, and then here, this is your D minus FO plus 1 over SI2. But guess what? When you do this, SI2, when that winds up back there, this is the definition of the back focal length. So this is the back focal length of the system, of the two mirrors. So we can write this as 1 over FC is 1 over D minus F0 plus 1 over F back focal length. So now let's solve for the back focal length, and we've done something like this before. So this is kind of with lenses, so the formulas will kind of be similar when we do this. So 1 over FC minus this piece is 1 over FB. So the 1 over FB is going to be, we're going to basically combine these two things together. So FC and D minus FO. So there'll be a D minus FO here minus FC. So these will cancel here. That's your 1 over FC. And then your FC's cancel. That's 1 over your D minus FO, and there's a minus sign there as we're subtracting. So that means here, if we flip it, the back focal length would be FC, D minus FO. We're just flipping it. And then D minus FO minus FC. And this would be FC. I'm going to multiply top and bottom by a minus sign since I know that FO is big. And then this becomes FO plus FC minus D by multiplying by minus sign. This flips, and then the D gets the minus sign and the F's are positive. But this is now very nice engineering. Watch this. If you take the D plus the U, that is the back focal length, because that's the distance from the second element to the point of focus when light comes in initially in infinity. So therefore this is D plus U, D plus U. And I get myself a real nice engineering formula that relates the parameters in the design. And I'm going to stop there. That is a cool formula, all right? Very nice.